Hey guys, thank you for coming. My name is Adam Thomas. I have invited a couple people to come and quote troll me. Hopefully they don't take that too literally. Anyway, my name is Adam Thomas. I lead the data science and sharing team within the NIMH, and I'm going to talk to you a little bit today about open science. Is that the right title slide? No, nope, that's too far. Open science controversies in neuroimaging. Now, if you were paying attention to your email, you might have noticed that this was supposed to be the crisis of reproducibility in neuroimaging, small n versus big N. And it was going to be Peter Manatini and myself talking about this, which seemed great. You know, I think controversies are great. I mean, the definition of a controversy is that two smart people in the field have differing opinions. And if you ever have the opportunity to have a conversation with someone and they're going to talk to you in good faith and be civil, and they disagree with you, I think those are the most valuable conversations you can have. So I was trying to get, I would be a big N guy, and I was trying to get some small N people to come up. Peter conveniently had to fly to Germany on Monday, so he wasn't able to be here today. So I'm going to do my best to represent both sides, but I filled the audience with trolls who can argue things that I don't see. So I have, at least I'll be playing trolls today. So I've been giving the Open Science and Neuroimaging talk as part of the summer series for, I think, 3 years now. All of those courses are available on the fMRIF webpage. It is a very typical, it's what I call my typical standard open science talk. So I'm going to give you a real fast forward. I think I see some summer students and some new ERDAs. So if you haven't heard the open science mantra, I'm going to give it to you real fast in like 3 slides. Okay, so the outline of that talk is, why do we need open science? What exactly is open science? And how do I do open science? And we're going to skip right to the take-home slide that is in that talk. And the take-homes are that science has a problem, the reproducibility problem that is evidenced by this Ioannidis paper from I think 11, 12 years ago now. But it's changing, and it's changing for the better. So that we can deal with larger data sets to address that reproducibility problem. And we're also changing our culture, where we're being much more open with our data, our methods, and our code, which leads into what open science is. Open science strives to maximize reproducibility and transparency in data, code, and papers. And we encourage, the community encourages everybody to try to embrace that. And finally, adopting open science practices has many benefits, including benefits in productivity, impact, and the reach. You can get out to more people. And finally, open science can be intimidating. It sometimes is a lot more work to do things in a standard and open way, and it can be scary. But you don't have to do it all at once, and you don't have to do it alone. There is, yeah, that's you, Paul. That's my same shirt. I thought you only have one. No. Here in the NIMH intramural program, my team, which is currently myself, Dylan Nielsen, and Travis Riddle, Travis is in the audience, Dylan will be joining us, are available to help you with any aspect of data sharing or open science in general. This email will go to all of us. There's a website, which includes our annual reports, which will give you an idea of what the kinds of things we do. We're in Building 10 on room 3D39. We have an open door policy. The machine learning guys are co-located right there on top of us, so you can stop by and chat. Within the next 2 months, we are going to be expanding. Dylan is moving to Argyris Stringaris' group, and we have hired Dustin, I don't know how to say that, Dustin Morkowetsky. And then we also have a really great ERDA joining us in September. We're also going to welcome the Scientific Information Officer, Asim Oker, who's going to be in the office next to us. So we are kind of the wing for all of your computational problems, whether they are straight IT, whether they are data science and data organization, or whether they're more complex machine learning algorithm issues. Stop by. We will help you figure out which problem you might have, and we'll give you a hand. Right, so the take-homes, we covered those, fine. Okay, and so that is the fast-forward version of my open science talk. If that is intriguing, if there's stuff that you want to hear more about, like I said, there's a recording and the slides available from that, all from last year. You can watch it on fast-forward, you can watch it on slow motion, do whatever you want to do. Okay, coming back to the controversies of reproducibility in neuroimaging, the small n versus big N question. So outline of what I'm going to talk to you about today. So first of all, how can one do reproducible science with limited resources? This was kind of at the end of my last bullet. Open science can be hard. There's a lot of things that you have to do more of in order to do it well if you want something reproducible. What are the strategies that you can employ? There's two parts to that. One is the perils of the pilot study, which I just love the alliteration, but it's basically about the futility of underpowered studies, and other options, things that you can do other than doing a study that is too small to show your effect. Finally, I want to talk about talking about reproducibility. This is something that came up recently, and there's active conversation going on in the community about the right way of talking about our reproducibility crisis, in air quotes. Is science broken, or is it something less than that? Okay, so most of the material that I'm going to present today is borrowed, adapted, and/or stolen from two sources. One is a paper from Russ Poldrack, which initially started as a blog post. It's called The Cost of Reproducibility. That was a NeuroView in Neuron. The last part is from Kathleen Hall Jamieson, and she is at the PNAS and was speaking about talking about reproducibility. So both these papers are available, and like I said, these slides will be available too, so you can follow up on these topics. Okay, how can one do reproducible science with limited resources? So I want to sort of set up something. I'm actually going to quote directly from Poldrack's paper. So imagine you are a graduate student. Maybe some of you don't have to imagine that. And you desperately want to do fMRI research, but your mentor doesn't have a large grant to support your study, and you have limited time. So you cobble together funds to collect a data set of about 20 subjects performing your new cognitive task, supporting some theory that you or your mentor has, and you wish to identify the whole brain activity pattern associated with that task. Great, very common story, seen it 100 times. Then you happen to read Scanning the Horizon, which is an article that was published by Russ Poldrack, among others, which argues, in my opinion convincingly, that the likelihood of such a study identifying a true positive result, if it exists, is very low. And the likelihood of any positive result being a false positive is high. And there's a paper from Button et al. In 2013 that makes this argument in more detail. And this is even if the study was fully pre-registered and there is no p-hacking involved. So that's pretty deflating. And I think, I mean, there are certainly people in the audiences that don't believe this. And I'm not giving that talk. If you want to read the Button talk, if you want to read the Button paper, if you want to talk about this in the discussion sections, I got two statisticians to come here, and we can talk about how true this is. Yeah, please. Sure. Yeah, absolutely. So, p-hacking. So you know what a p-value is. So p-value is to, do a test against a p-value. So it is the practice of p-hacking is that if you do a test, you pull your data together, and then you test it. It says, is this significant above 0.5 or 0.01? And then it's not. And you say, maybe I'll change the smoothing kernel. And you do that. And they go, well, maybe I need to do the motion correction differently. And you do that, and it's still not significant. And then you do that multiple times, right? And then eventually you find the golden little set of preprocessing parameters or statistical parameters or what have you that gets you the significance. But from a statistical point of view, you've completely invalidated that p-value because you have to correct for every time you try something new. So a lot of the argument from from the community is that the literature is full of analyses that have been p-hacked, so many of the things that we think are true are not. Clear? Okay, cool. Like I said, so if we want to talk more about this, we can hit it in the discussion section. But what are you going to do? You want to be an fMRI scientist. You want to collect some data. You want to do something. So I can tell you what the most common answer to this is. You do a pilot study. It's like, oh, yeah, you know what? We'll just get 5 or 10 people. We'll throw together some stimuli, and we'll just poke around a little bit. Maybe something will pop out. Maybe we'll get something maybe we'll find that super big effect. So I would like to argue, don't do that. I would also, so if you read the Poldrack paper, it's also making the same argument, that pilot studies are basically setting you up to conduct an underpowered study. And even in the best scenario, that doesn't work out well. And when you're doing a pilot study, you kind of have this thought that I've heard from a number of people saying, can I just focus on big effects? So I hope that we can all agree that all experiments need power. You're not going to detect anything if you don't have statistical power. Statistical power boils down to, well, it's a lot of things, but the three things that are most important is your chosen threshold, p less than 0.00 whatever, your sample size, the number of subjects or the number of trials or whatever it is you're going to average over, and your effect size. So there is, well, I'm sorry, I'm naming names. A lot of people say, well, I'm just going to focus on big effects. I don't want to collect 1,000 subjects. I don't have time to collect 1,000 subjects. I'm going to go look for the large effect size because those are the most interesting things. Indeed, if you ever hang out with Alan Koretsky, who is the NINDS former scientific director, in a bar late at rock bottom, he'll tell you, big data is for small effects. I'm only interested in big effects. And I've been in this argument, and I should say now that Alan Koretsky is an extremely smart guy. He's got more talent than his little pinky than I do, but I'm going to tell you he's wrong. So adjust your priors appropriately. Okay, so let me tell you a little parable about a pilot study, about the whole idea of searching for big effects. So say you're this graduate student, you've decided to do a pilot study, you've got your cognitive task, maybe you're looking at face areas, maybe you're looking at motor areas, and you're just playing around a little bit. First subject goes again, you go through the analysis, you look at your contrast, and then you threshold it, and you see the face of Peter Bandettini. Right there in the parietal lobe, you see a full rendering of Peter Bandettini, going, wow. Well, that's pretty unlikely. I mean, this is like 05, right? So, I mean, it's only one subject, and, we only got 20 runs, but I mean, it's the face of Peter Bandettini, right? It's like, what? That's crazy, right? But I can't ignore it. It's right there. It's like, well, I should try again. So you're on another subject, and there it is again. Slightly different region, but there on the brain is the fully rendered face of Peter Bandettini. So you're thinking, it's like, wow, I don't even know how I designed a statistical test for that. It certainly wasn't in my hypotheses beforehand, but I can't ignore it, right? I mean, like, what are the odds of this happening twice in a row? Two different regions rendering one of the fathers of fMRI right there on the brain. It's like, well, he discovered fMRI, and this is the scanner that he maintains. Maybe it all makes sense. Maybe there's a dedicated region for representing Peter Bandettini's face in the cortex. Right, so you're in a conundrum. There are different paths that you can go to. One of the things that you might do, and which is frequently done with effects of this nature, is that you might just publish it. Right? I mean, you could call it the putative PAB area. You could contact the high-profile journals. And you could say, hey, this is an exploratory study, or maybe you're going to say that you actually hypothesized this. That happens sometimes as well. But you could probably get that into a journal. Another option is you could try to validate it in an independent data set with a strong pre-registered hypothesis. Can you find Peter Bandettini's face in the HCP data, for example? Or maybe you're going to contact somebody in another lab with a different scanner and a different pipeline and says, can you see this as well? So when we see these surprising findings, I mean, this is obviously an extreme example of just for silliness, but a lot of times we find a finding that doesn't really pass any statistical test, but it fits so nicely with our preconceptions, and it's also very exciting, but there's not really any way to say that it is statistically valid. So we run with it, right? I would encourage you to do the other thing, and try to validate it in an independent data set. And doing these things, I mean, I think when people sit down and try to focus on finding big effects, they're basically looking for the face of Peter Bandettini. They're looking for something really unusual that's going to pop out, that's such a strong effect, and so obviously meaningful that it's uncontrovertible. Some people call it the ocular trauma test, because it pops you between the eyes and it's completely, you can't deny it. If you stumble on one of those effects, thank you, lucky stars. They are out there. It happens. There are amazing serendipitous moments when somebody finds something amazing, but it's relatively rare. So when you're trying to decide and plan your study, it's very hard to estimate your effect size in advance. So if you're just trolling around, you might stumble into one, but you're more than likely not. It's also very easy and common to overestimate effect size. So when you're calculating your power to see if you have enough power to do this study, you should look at that number very conservatively. And you should design your study to plan for a more modest effect size. A lot of the best studies basically have two questions. There is that really high bar crazy thing that you're asking. It's like, I kind of think this might be the case, but I'm not so sure. But there's this other thing that I think is more likely to be the case. It's less flashy, but it's certainly an important question that is publishable. Those are the kinds of things that you should be designing. Dan?
Hey, is this working? Is
Not
this
yet.
working?
Yeah, now it is.
Okay, so this is the first official heckling, but we were asked to heckle for the people who came here late.
Please.
So I feel like you're confounding a little bit here effect size with a priori hypotheses, and there is a difference there. So if you're going into a study saying, I expect a PAB region to appear in this part of the brain, and I expect it to be big, that's very different from saying I expect something big to be somewhere. So, I put an N of 1 on a flashing checkerboard. I know I'm going to get Cachren sulcus, a big effect, and I can see it in every time I scan someone for 5 minutes with the checkerboard.
Yeah.
So, so there's this added constraint of not just effect size, but also what you're expecting to see.
Yes.
And that narrows down this a lot more. I think the types of study that you're pushing back against is, I am doing a task and I want to find the brain region of X when you don't have an hypothesize what that brain region is. So you're saying, I'm doing something and somewhere in the brain will probably activate in this region. I don't know where it is. Those are the ones they're going to get in trouble with.
Right.
But if you're saying, I expect the amygdala to vary significantly between condition A and condition B, you're much more narrowing your hypothesis than sort of this, I expect something somewhere.
Yeah, you're definitely right. I am mixing those two issues. And the argument from the button paper and from Poldrack is that even if you do have a specified hypothesis and even if you do pre-register and do no p-hacking and do all those things correctly, 20 subjects is not going to get you there if you're doing a whole brain analysis, right? But yeah, this is definitely tying those two things together, because I think in the average pilot analysis they are doing both. They have weak hypotheses and they are underpowered.
But there are also dozens of small N studies that have held up, like, the face-place network, some retinotopy, all these working memory. These were all small N studies, and they were replicated not in the same study, but in future studies.
Sure, but proportion. I mean, let's look at all the small N studies that have been published over the past 25 years, and let's look at the ones that replicated, like face area and like Cachren, and then the ones that didn't. I think you'd be in the single digits.
But that's part. The question is it better investment to have more of these small studies, of which 10% replicate, or having only 10% studies, of which 30% replicate?
That is an excellent segue.
You're welcome.
Go ahead.
Just a question regarding effect size.
Can somebody pass that guy the microphone? We're recording.
Sure. Thank you. Just an ignorant question about effect size. Do we assume that there are no special caveats for estimating effect size with the statistics or the tests that we would perform for fMRI, as opposed to just a normal two-sample t-test? Is there something about the interclass correlation between different voxels or different groups that might affect or bias that special consideration should be taken into place? Because I don't know how to do a power analysis for fMRI.
Sure. Power and the power analysis are going to vary depending on what analysis you do. So the button paper and the Poldrack comment is basically targeting what was the bread and butter of neuroimaging for 25 years, which is just a massive univariate analysis. I'm going to look all across the voxels. I'm going to form some clusters. I'm gonna test some theories. And yes, you're right. There would be some tweaks depending on how many contrasts you have and how much smoothing you do, but the argument that is for the most common analysis, you have no hope with 20 subjects. But yes, I mean, so and I'll get to this. Like, there are more focal hypotheses that you could make. Like, if you're making a hypothesis about a specific brain region, you're reducing the number of voxels, or you're gluing them together into regions of interest or things like that. There are other ways of getting around this, but the argument from a lot of these papers is that those ways are less common in the literature currently than the alternative. Okay, anything else? All right. Right, so this is a little figure from the button, I think it's the button paper, about the effect sizes that exist out there. So it's a distribution. There are large effects, there are small effects, and there's a lot of things in the middle. If all of us only looked for big effects by doing a whole bunch of small studies, there is a whole bunch of stuff here that we will never know about. And I think that stuff is important. Okay, so if I've come close to convincing you that underpowered pilot studies are a bad idea, what else are you going to do? I mean, you've got 3-4 years for your graduate program. You've got a lot to learn. How can you get your career going if you can't do a small study? And I'm drawing directly from Poldrak's paper. So one of the answers is pivot. So he uses Nancy Cambusher as an example here. So I don't know how many fMRI people there are. So Nancy Cambusher is credited with discovering something called the fusiform face area in the mid to late 90s. There's a little chunk on the bottom of your brain that lights up when you see a face. It is one of the most reproducible effects in neuroscience, or in neuroimaging. Almost anybody, regardless of how bad their analysis stream is, can get the fusiform face area. Even though it's, I mean, like you can, obviously smaller, like lower perceptual things, like Dan was saying, if you're looking at V1 or motor, those are quite replicable. But fusiform was arguably cognitive, and it was the first thing that really nobody could doubt, because anybody who tried to replicate her result found it. So she's a good illustration of doing reproducible science. But I'm going to read this to you. This is her quote from this paper that she put out in J Neuroscience. I had never worked on face perception because I considered it to be a special case, which is the narrative that we have now, less important than the general case of object perception, which is what she was interested in. But I needed to stop messing around and discover something, so I cultivated an interest in faces. To paraphrase Stephen Stills, if you can't answer the question you love the question you can. So I have definitely been in a number of lab meetings where a new person in the lab, whether it's a post-bac IRTA or a grad student or a postdoc, comes and they present a study, and there are dozens of conditions. They're excited about so many questions, but you can't do that. Like, the more questions you ask and the broader they are, if you're asking across the brain or you're asking across the entirety of behavior, you can't do that with 20 subjects, or you can't do that with most of the subject numbers that you would get in a typical graduate degree, unless your mentor has an army of staff to collect that data. So the argument is that there are plenty of questions that you can ask if you narrow your focus a little bit. And if you want to figure out what that power analysis is, and power analyses are not straightforward. If you don't know exactly how to calculate it, this is what we have great statisticians for, like Gang Chen and Charles Zhang. Talk to them before you dive in, and make more modest hypotheses. Asking a more narrow, tractable question is a great option, but be sure to publish it, even if it is a negative result. If it's well designed, and if you go so far as to pre-register it and say what you're going to do, it is very publishable. It might not put you in Science, it might not put you in Nature, but it is going to contribute to science in an important way. Paul.
I was going to ask about negative results and how those come in, because surely that's a huge aspect of something that's missing in the field that you.
Your mic's not on. But I can repeat. So
Okay,
he was asking about negative results because that's a huge aspect of something that's missing in the field. Yes,
I'm not convinced that they are publishable in general. And another thing with pre-registering results, how do you pre-register results if you're using publicly available data because it's always been collected? That's a slightly separate question, because a lot of people will be doing studies in, like, your, let's say you want to test something out in 3 different subject groups that are independent, then you can do that with open data, because you're probably not going to acquire that in a 3-year period on your own.
Right.
So that's a separate question as well. But if it's not pre-registered, I don't know that you can publish a negative result. And lots of the data that's available now, I don't know how you can pre-register it because it's already collected. So let
me ask you answer those in turn. So yes, the absence of negative results in the literature is certainly a problem. But today, with the proliferation of journals, everything's publishable, right? As long as you are, so PLOS One, bioRxiv, PsycArchive, and yeah. So there's another. I'll touch on this towards the end. If your CV has nothing but archive papers on it, are you going to get a job? That's a totally reasonable question. I'd like to table that for another section. But you can get it out there. You can get it out there in in whatever form that it is. And there is also, this is part of my other talk as well, is that there is an amazing increase in the acceptance of preprints in archive or bioarchive. You can now cite them on grants. Francis Collins has gone on Twitter and gone on stage and said, all of my postdocs put their stuff on archive first. Preprints are the way of the future. So if it doesn't get published, that's unfortunate, but if it goes into the file drawer, that's much, much worse.
I mean, preprints have existed in other areas of science and been successful. So it's just the fact that this part of the science is very late to the game
Agreed.
on that.
Agreed, yeah. No,
But
physics and math and
but I-
whatnot have been ahead of the game for a while.
I'm still not convinced that those are treated in the same way if you're doing like a general study. You know, if someone publishes something in Neuron, I'm not sure that result will ever get bumped by negative findings in a bioarchive in the same, unless it's like a million of them, but I'm not sure that'll be done. And I'm still not convinced that negative results are treated in a comparable way to get pooled in, and I think that's a
Well, I
huge
mean,
problem.
and they shouldn't, right? There's a lot more ways to get a study wrong than to get it right, right? So if you're publishing a negative result, you need to go to the extra effort to convince the reader that you didn't just do something stupid, right? You got to put your code up there, you got to put your data out there, you got to put all the things you tried.
That burden of proof applies equally to positive and negative results, I think. I mean, shouldn't that?
I disagree. Well, I mean, it should in a perfect world, but I could name a dozen papers in high-profile journals that were highly lacking in data to support their claims, but the claim was sexy. They don't see that with negative results. You don't have an amazing front page negative result that is poorly supported.
No, that's my point. Yes, that is a problem.
Yeah. So you do have to work hard. Yes. So I think I agree with you on all of the things. I guess maybe where we differ is I think it's getting better. And there's a path to a better situation. There's one more bullet here. Asking narrow, tractable questions is a great option, and publishing negative. Oh, no, sorry. There was another thing in my head. I had another question. Dylan. Yes. You're off. There's a button.
Hello? Yeah. Hey, I was just going to answer Paul's question about pre-registering
reference.
data on publicly available data sets. Most of the time you do a pre-registration, there's no one checking it. The pre-registration is essentially you writing down and timestamping the analysis that you did and the analysis that you did prior to pre-registration. It's on your integrity as a scientist to do that honestly, and the extent to which it is a compelling set of information for the reviewers depends on their evaluation of what you've written. So you can absolutely say, I'm doing this analysis on these 3 publicly available data sets. Here are the things that I know about these data sets going into it, and and this is what I plan on doing from this point forward. So you absolutely can pre-register and just disclose and be honest about what you have done with those data sets prior and what you know about those data sets going in. And it's another tool for convincing reviewers that the story you're telling is an honest and true one.
Yep, that was exactly what I was going to say. Also, if you want to form some hypotheses and you don't have the data set to, I mean, exploratory analysis are an extremely important part of science. So when you say a pilot study is a waste of your time, it is okay to do an exploratory analysis on a hypothesis that you haven't totally worked out. But a lot of pilot studies that I see end up taking 3 years of the graduate degree, and then they end up having a thesis saying a pilot study, right? So if you can, try to test your question on a shared data set, or try to test a question that is related to your question on a shared data set. So then you can dive right into the analyses and play around, and you don't have to spend 2 years scanning subjects in the basement of Building 10.
So,
Yep.
but, using the anti-Camwisher example, how are you going to find the FFA if you're not using tasks that are designed that are supposed to identify a phase-selective area? I mean, you're assuming that that there's a shared data set for every sort of cognitive contrast.
No, I'm not assuming that. Yeah, I'm not saying that in every case the question that you care about is going to be available in a shared data set. But I'm saying that at the beginning of your career, think about a variety of questions. Don't come in and say, I only care about pictures of Peter Benettini in the amygdala, and that's the only thing I'm going to look at, right? Define your space broadly, and then look around and think what's tractable. That's a huge part of science, and that's what the Kamwisher thing says. So she stumbled on the face area. She didn't go after it. She was looking at things that were not tractable and kept on saying, wow, this huge blob here that keeps on hitting me in the face. So if you start doing that with a shared data set, or maybe on an old elder postdocs data set, maybe something's going to trigger your interest.
But even still, like, I mean, Nancy Kamwisher, 90% of her career has been small n studies. She made her name on these small n studies. Russ Poldrack made his name on small n studies. I mean, it's sort of a nice idea in theory, but I have trouble thinking of a single successful faculty member who didn't gain their reputation on small n studies. For people who are actually collecting data. For people who are just sort of using data out there, that's a different story. But if you're saying data collection is part of what you're doing, I'd have to think long and hard for someone who didn't sort of come up either in a well-resourced lab or came up by building reputation on small n studies.
That's totally true. This bit in the end, and Poldrack talks about this in the last paragraph. But the caveat to that is, it's in the past, right? There was a number of things we did in the 90s that were stupid and unfortunate, and a number of people benefited from unfortunate choices. And the ones that are most ethical are now publishing follow-ups saying, like, oh, this paper was methodologically messy, we're going to redo it now, and we think the curves look like this instead of this. Just because something happened in the past doesn't mean that it is your fiat to do the same thing again.
But that's science. Science is saying we did a study, it was replicated from several other studies to make it worth thinking of more, and now we're thinking about it more rigorously. That's not big N or small n. That's thinking through a topic. I mean, a lot of the stuff that Russ Poldrack did early has held up, but it's been there's been added nuance to it.
But not all of it, right? So he has a paper where he
course.
sort of goes through what did and didn't. So I mean, the other thing is that the
If it all
reviewer.
held up, that would be bad science as well.
What's that?
If it all held up, that would probably be bad science as well.
It would raise some questions,
Yeah.
right? So yes, so the people that started 20 years ago had some advantages that we don't have now. The things that I am preaching up here are not just me and Russ Poldrack. If you ever have the ability to attend NIMH Council, where they sit down and talk about all the money they're going to give out, no small n studies are getting funded. Right? You can do one. You can claim to do a big N study and then use the money to do a small n study. But the drumbeat for well-powered studies in the funding environment now is deafening. So I mean, there's a certain aspect to this that is not fair, but the world is changing.
Yeah. Let me also add on to Adam's point, which I did not come into this room to do, which is that open science and open data sets are relatively new, right? Like the massive studies, particularly.
Yeah, I mean, there's certainly way more of them, right? There were some back in the 90s, but there's so many more now.
And also the culture has changed. So the culture of science used to be, I'm going to hold my data hold my own cards. I'm never going to share it because heaven forbid I did something wrong, or I'm not done mining this data set. I hear that from a lot of senior investigators still, of like, oh yeah, I'll give you that data after I get my next publication out of that, and I'm still waiting 20 years from now. Right. Because the culture has changed, now there's this almost expectation, I think it's a good expectation, that people will share their data, and that then we can start to ask some of these questions. And again, I can't believe I'm taking the side of the argument. I meant to come in here with the other one.
It's okay. You'll have an opportunity to troll me later, I'm sure. Yeah, and so that's also something that you'll see if you read Josh Gordon's papers and blog posts. Data sharing is not an option anymore. If you get NIMH money, you are required to put it in an archive. Now, if you want to be difficult, anybody can obfuscate their data enough that no one can make any sense of it, and that certainly happens. But the argument is that your program officer will eventually notice, and that will catch up with you. So, I mean, in general, I think that advocating for data sharing should be focused more on carrots than sticks. But that's not to say there aren't sticks out there. Yeah, Gang.
Right. So my perspective is from modeling.
From modeling.
From modeling perspective.
I'm not
So
sure your
I-
mic is close enough or on.
All right. So I think a part of the problem, like a reproducibility crisis and p-hacking, I think is based on the current modeling approach. I think we still have a lot of room for improvement in modeling.
No question.
So I mean, those problems can be improved through modeling perspective. So if you do have enough resources, of course, go for it. Big N, whatever, open science, yes. But if your resources are limited, I think we can still do a better job
Absolutely.
by improving the modeling perspective. For
You've
example-
anticipated my third point.
Yeah.
Or, sorry, I should say Russ Poldak's third point.
For example, the current approach, the massively univariate modeling, that I think there is a lot of room for improvement to do that.
Absolutely.
The
And if you go-
current crisis, the p-hacking is related to that issue. So that's one perspective.
And we're getting better, right? Like if you go to HBM today, I mean, it's far harder to find the standard mass univariate approaches. Most everything is connectivity, which obviously has its own set of problems, but at least we're making different mistakes.
Right, the crisis or the p-hacking, why people do that? Because the modeling is not doing a good job. That's my.
It is certainly among the things that are wrong. It's a multifaceted problem.
The second is the current climate, the culture is that they emphasize the stringency by setting a threshold. So they force people to dichotomize the results. That's like you set a sea level, anything above the sea level, yes, that's acceptable. Below the sea level is considered non-existent.
Right.
That's just not right. The nature, I mean, whatever we deal with in the brain is a continuum. It's not dichotomized. So that culture is just not beneficial. That's why people do p-hacking. If we allow full reporting, then you can highlight the results based on whatever the currently acceptable criteria. But at the same time, you can still report the results under the water. That's fine. That doesn't mean they don't exist.
Sure.
That's part of the problem in the current culture.
Yeah, I don't think anybody is advocating for hiding data that's not under threshold. But there is a really active debate. This would be a great lecture that I'm not at all qualified to give. There was an opinion piece that was signed by a couple dozen different scientists saying that we should throw out thresholding, the argument that that Gong is making. And then John Ioannidis came out and said, no, I think we need it. And above my pay grade, guys. I think Ioannidis is a really smart guy. I think that Gong has a really great point. I don't know what the answer there is, but this is an active controversy debate in the field right now. Mackenzie. Sorry, I have your name wrong.
Chandler.
I did that before, too. Those aren't similar. They've got lots of syllables. Please, Chandler, go ahead.
So this is less of a question, more just I'm having trouble consolidating a couple thoughts in
Please.
my head. So I feel like on one hand, you are arguing that to further an individual's career, it is important to do studies that have lots of people. Small studies are not going to have as much power, therefore are not going to be as publishable, therefore you won't get the funding, et cetera, et cetera. But at the same time, I feel like there's so much that happens in the brain. It's such a complicated system that these smaller studies, even if they do not have the greatest power, are pointing us in more directions to look. And that is why negative results are important and why you should publish them.
So there's two things in there. So the Button paper, and to some extent the Poldrack paper, would argue that they are not pointing you in, if the study is truly underpowered, then it is not pointing you in the right direction. It is almost certainly pointing you down a rabbit hole. And so you should be careful.
Away from a wrong direction.
And so so power is complicated, but if it is truly underpowered and these clever statisticians say your study is overpowered, then you should not interpret anything from that, right? But it might be sufficiently powered even though it has few subjects if you have a giant effect, right? Like if there's something that is just, again, ocular trauma, you can't ignore it. You can get a powered study with one subject. And the other thing, again, I'm dipping deeper into my points, is thinking like a visual neuroscientist. So if you take one subject like Javier Gonzalez-Castillo did and scan them many, many times like visual neuroscientists are known to do, you get the power. You can't make a general claim about the entire population, but you can say, this particular brain is really interesting in doing these things. Maybe it's saying something about other brains in the population.
Yeah, and then I guess on top of that, there's also, we do have limited resources, and we're not just talking about individually, just overall fMRI machines are expensive. They take a lot of time to use. A lot of people with good questions and who are good at science do not have access to them, which makes it difficult to do big science in general in this field, especially because a lot of interesting questions now are about smaller populations, like let's say you're working with depressed patients or children with autism, those kinds of things. It is just very explicitly difficult to get the number of people you would need, but I think those are still important questions to ask.
Yes. So the argument from that I am parroting here is that those are very important questions, but if you are not powered to ask them, you're doing the field a disservice. There's an article in the Atlantic that just came out that was a popular press version of a study that said there's a set of depression genes that we have been studying for 20 years that has some hundreds of publications on it and untold numbers of millions of dollars. None of them have anything to do with depression. So the genetics community is 10 years ahead of us on this, right? So the genetics community started getting together and pooling their data. Their data is much more strongly typed too, so it's a little bit easier. But when they got together a sample of hundreds of thousands of people, none of the genes that these people have been studying for the past 20 years have anything to do with depression, right? So much wasted money, all because of underpowered studies, right? So I'm not saying these questions aren't important, but don't ask them if you don't have the tool to ask them. I mean, and we are getting better at pooling our data, we're getting better at collaborating, we're getting better at building studies that are powered, but there's still a lot of studies that are published on a daily basis that don't have the power to make the claims that they do. Cool. All right. Pivot, yep, okay. Oops, what did I do? Oh, collaborate. So I think I've hit on most of these points in the course of the discussion section. So if you read the paper, I mean, it is, you might be surprised if you reach out to a paper that you're reading that has intrigued you and say, I have this idea about your data. I am interested in analyzing your data to explore this hypothesis. And if you want to be generous, you can say, I'd be happy to include you as a co-author, right? Or you might, so meta-analyses, right? I was contacted by someone who said, hey, let's combine all these data into a big meta-analysis. Scientists can be introverts. A lot of times they would rather just maintain control and do their own thing, but the paper is basically arguing and gives several successful examples of collaborative science where you pool the data sets and find things that the original papers did not. You share data. I feel like we've hit that one pretty thoroughly. Embrace theory, which I think this is kind of what I was thinking with Gong's comment, is that a lot of the hypotheses in neuroimaging papers these days are extremely rudimentary. We do not understand how the brain works, part of Chandler's point. We need models, complicated models, about the way the different regions interact. And it is entirely possible to spend your entire graduate career testing the models that are out there, honing the models that are out there, and developing new models just by reading the literature. I mean, I think a lot of people don't think that is the fun part. I mean, there's something exciting about sitting in front of the console and getting brand new pictures of your own data, but there's a huge need, which is argued in this paper, for more theory and more computational modeling. And I guarantee you that if you come out of your graduate degree having some chops in computational modeling, you're not going to have trouble getting a job. Maybe it's in science, maybe it's somewhere else, but you will be very well positioned. We touched on this before. Think like a visual neuroscience. Big N doesn't have to mean people. You need to get your study powered, but that can mean that you do 100 trials on yourself and your graduate student. Harder to do in the NIMH, but you can get a small sample size and you can characterize them very, very well. Slightly modifies the claims that you can make, might slightly modify the journals that you can get into, but like I said, visual neuroscientists have been doing this for 100 years, and we've learned a great deal about that. I mean, we don't understand the brain, but the visual system is definitely getting closer than the rest of it. They've made a lot of progress with this approach. Yeah, so this is just what I was saying. So there's a paper by Philip Smith and Daniel Little that makes this argument, that small is beautiful. People point to this as sort of a counter to Russ's claim, but Poldrack wouldn't disagree with this. This is definitely a totally valid way of doing science. Okay, so that is all of the recommendations in this paper. Are a handful of other things that I'm only going to touch on briefly. And this is, again, I think, Russ Poldrack answering a lot of Dan's points. The incentives are not yet aligned. If you throw your ethics out the window and try to get as many Nature and Science papers as you possibly can, fudge stuff, hide stuff, still the case today that you might get ahead. You might even have a better chance of getting ahead. But you might have trouble sleeping at night, right? So there's an argument basically that things are changing, that you're starting to see more incentives for data sharing. You're starting to see more incentives for transparency. John Ioannidis has an article where he sort of like looks at this in the literature, and there are quantitative arguments to see that they change, but I'm not going to lie to you, it's slow. We are working uphill against a very entrenched idea of the way biomedical research should be done. I have been in this team for, I think, 3 years now, and I'm now heartened by when people come into the lab and I try to explain what we do, and I try to explain the principles of open science. They go, "Isn't that just science? Why would anybody? Do people hide their stuff? Like, the new generation just doesn't occur to them that this might be happening. So that gives me hope that maybe the progress is going to happen generationally, right?" He also advocates for making your efforts known. If you are doing these things, if you're making pre-registrations, if you're sharing your data, if you've got a lot of stuff on GitHub, let people know. You can have an entire section in your CV. I'm starting to see this more often than not, that there is basically an open science section where they say, here's this code, here's this tool, here's this database, or here's all these things that I've done and I have made freely available. Some of them might have DOIs, some of them may have been ignored, but you can still provide a list of the things that you've done. And I can say with some certainty that if a program officer will look kindly on those. I don't know about tenure committees, but it certainly is becoming more important in program. And the other thing that Russ has a paragraph about is ladder pulling, which is precisely Dan's comment, that everybody who is at the top of the field now, who has been here for 20 years, has some skeletons in their closets. They have some papers that were published that were underpowered. And some of those papers are very well cited, and some of them are still driving their careers, right? Every once in a while you see someone like Russ Poldrack who says, actually this one, not true. Or every once in a while you see something like the depression thing where somebody else comes along and says, actually all of those are not true. So I'm not saying that there will be a great reckoning where everybody who published a small N paper will at some point have to deal with it. That's not what usually happens. But I am trying to argue that that the field is changing, and that if you are a pioneer in that, you will be recognized. You can believe me or not. Okay, so this is a pivot talking about reproducibility. Did anybody have questions on the other section? Because this is kind of different. Go ahead, Dan.
I'll add one more general kind of meta comment.
Please.
On the embrace theory, one of my long concerns is sort of what does it mean to educate the next generation too. And a bunch of years I sort of made this sarcastic prediction that with the rise of resting state, you'd have a generation of psychologists who have never designed or run a task. We now have that generation. Mm-hmm. And now we're getting to the point where we're going to have a generation where most of them have never seen the inside of a scanning room, let alone collect the data. And part of designing theory is sort of being in touch enough with data acquisition, data collection, experimental design, that you know what something means beyond just what you read in a summary in a paper. And some of these smaller studies, there's this educational component that goes beyond the findings in and of themselves. And I don't have the good answer of how to sort of say we should do a bunch of lousy studies as an educational issue. That's the wrong answer. But I think it is concerning that there's more and more people who don't have those critical skill sets to design the studies and think about the theory because they've never actually done kind of that lower level conceptualization of study design and data collection.
Sure. No, that's a really good point. Several things. So, first of all, there's too many things to learn, and there's not enough hours in the day. Ultimately, We all need to specialize a little bit. We can't do all the things. There are plenty of people that would argue, or I've stumbled upon people that argue, like, how can these people do science when they can't do any pulse programming, right? there's a lot of physicists who think you need to really understand the fundamentals of maybe you're one of them, I don't know. But I don't have a sophisticated understanding of pulse programming. I know a lot of people don't, and they still manage to do good science. There are also plenty of computational neuroscientists who are very successful and don't really have a lot of familiarity with prep. Now, the most successful thing that you usually see is a pairing. So Dan Butts from UMD comes over here. He hangs out with the NEI and the Laboratory of Neurocognition things, and he has a whole stack of computational models. Do you want computational stack? I don't know, whatever. And he basically has a dialogue with them. I think weekly or monthly, saying, okay, I ran that last data you gave me. I made these predictions. Here's where the model fits. Here's where the model doesn't fit. I would really like to test this. Could you do these particular experiments? And they've been going back and forth like that for years. So you've got one guy who has a really intimate dialogue with the empiricist, and the empiricists have at least a conversational understanding of the computational modeling, and that's how the science moves forward.
I mean, I definitely agree on sort of specialization, but I'm concerned where that next generation of empiricists is coming from. If we're down
You're concerned with the next generation of what?
of sort of data collection empiricists, if we're downplaying study design and acquisition too much across the field. I mean, like individually, like yes, one person doesn't need this, one individual doesn't need this, but as a field, I feel like it's getting a lot more down. Like it's like the skills of the psychophysicist, which was like really precise experimental design, is almost dead in the current generation. And
I think if you go to VSS, you might find some people who would argue with you.
Okay. But it's definitely shrinking, the well-designed studies, and I'm concerned that like what happens if that part of the trend continues, that you're not going to have that empiricist who can do the experiment well. There's a bigger question.
Yeah, no, but I guess, I mean, I don't agree. I think when I look at study design over the past 25 years, I am very convinced that it's gotten better. It's not clear to me that we have lost this skill. There's still plenty of badly designed studies, but a lot of the data, a lot of the public papers that are being published are now, maybe they're using a little bit, like Emily did, right? You use a little bit of the data that you collected, and you use a little bit of the HCP data, or the UK Biobank data, or the ABCD data. And if you sit and analyze that data, you're going to learn a lot about study design. You might actually think that they did a bad job, right? But you're going to say, wow, I can't ask this question because you did not deconvolve these two conditions. That's annoying, right? I think that skill is alive and well. I mean, psychophysics is not what it used to be. There's a lot of causes about that, but I guess I don't think it is because people don't know how to design studies. This is controversy, guys. We got people having civil conversations with different opinions. It's great. Talking about reproducibility. Are we ready? Cool. Okay, so this bullet point came out of a talk. Excuse me. This was it's a workshop, I guess, that was hosted by the Proceedings of the National Academy of Sciences. So if you don't know what, excuse me, not the Proceedings. The Proceedings is their journal. There is the National Academy of Sciences, which is kind of like royalty for scientists. It's a very selective organization. It's crossed a number of different domains, and they have very important roles in advising the government and the world about what's going on with science and what should be going on with science. So, for example, President Bush asked them to write a report about climate science back in the early 2000s. So it is an organization that cares about science written large. So they hosted this workshop on April 29th of this year. Our very own Peter Banatini was invited there, and it was called Establishing the Trustworthiness of Science. He asked me for some slides. I gave him some of my standard data science slides, thinking it was going to be another, yay, open science talk like I've given so many times. But they were making a very different point, which I initially found a little abrasive, but I came to think is important. So that's not the right one. Oh, yeah. Well, no, we'll start with this one. Okay, so this is the paper from Kathleen Hall. Is it Danielson? I'm not sure what it is. Crisis of Self-Correction, Rethinking Media Narratives About the Well-Being of Science. I'm I'm going to put off those other two. So this paper is targeting a lot of people who have published papers that are basically in the same vein as what Ioannidis published way back in 2005. So this title was inflammatory, and it got a lot of people upset. And obviously, that's kind of what you do in titles. You want to generate a certain amount of controversy. You want to generate a conversation. But the argument from Kathleen and from the PNAS in general is that you need to think about the repercussions of this kind of narrative, right? So without getting into too much detail, the United States is in a culture war. There are plenty of established science facts, vaccines, climate science, what have you, that there is a majority of the United States that thinks they're not true, right? So their argument in this paper is that if you start publishing papers, which then find their way into the popular press, that say, science is bankrupt, there is a world in which that has a hugely negative impact on science, right? And it's a challenging argument. I think this is really an interesting controversy. Like, so we are scientists. We have cast our lot in with brutal honesty. We're going, like, John Ioannidis does not think that that title is wrong, right? He thinks that that is totally accurate. I mean, you can argue about whether or not it is, but he was not. I mean, it's short and punchy and inflammatory, but it's not different than what he actually thinks is the case. But so what the PNAS, the Academy would argue is that if you're going to point out problems with science, that you should point out that science is a system that is self-correcting, which is kind of similar to, I think, the point that Dan was making, that we have made mistakes throughout the history of science, and that they will eventually figure themselves out. If you say that it's broken, that it's a crisis, that it's completely bankrupt, and all of the stuff that we've ever done is useless, I mean, what are we saying? Do we want to start a revolution and storm Building 1? Burn down the NIH? So, I am actually genuinely torn between these 2 points of view, but I did not seriously consider this other point of view until I watched this workshop. And so these other things that I linked in here, these are to a book and an article from Cass Sunstein, which talks about social change. So he talks about revolutionary events and sort of the new phenomenon of going viral. Now that we have Twitter and Facebook and all these social media things, it is very possible for someone very low on the pay grade at NIH to tweet something, and suddenly it goes viral and has a huge influence on the course of history and the funding of science. So anyway, I think that I can make both sides of that argument, but I think it is an interesting controversy. So a lot of people think that the open science advocates on Twitter and what have you are trolls, right? They're basically just throwing shade on people that are trying to do good science. And it's an important thing to remember that we're all here trying to do good science. We can civilly and constructively point out things that are wrong without sort of burning down the house. And so this is also related to a lot of what the cluster failure argument that happened 3 years ago, right? So there was an inflammatory title that was published in, I think it was in PNAS, and it caught on. I mean, there was really a point where they were saying, like, okay, let's just stop funding fMRI altogether, right? And again, I'm not sure that Eklund actually disagrees with what he's saying, but there's an argument to think it through. All right, so take-homes, we're at 3 o'clock. Running underpowered studies is frustrating and futile. There are alternatives. It's possible to design reproducible neuroimaging studies with limited resources using shared data, using targeted questions, using collaboration, and using subject-centered design. When talking, tweeting, publishing about problems in science, take a moment to consider what you're arguing for. Take a moment to think about the potential downsides of your message before you do it. All right, thanks. We don't have a ton of time, but I'm happy to hang out. All the slides will be available online. Dan, you look like you. Oh.
I do have a comment. I'll make sure anyone else has a question first. But yeah. Anyone else? Please. Anyone else? So the one thing I'll add on to the last point, which is a complete agreement, but as someone who in other contexts is usually the heckling troll of complaining about all the problems in the field, There was a study in fMRI a decade ago now, the salmon study, where if you type fMRI and salmon, you will find hundreds of links. Just Google fMRI and salmon. And it was an educational joke. It was a joke poster at a conference where they put a dead salmon and they got a blob in the brain, and they said if we didn't do our our statistics correctly, we see activation in the brain, but if we do it correctly, we don't. And it became sort of a paper that was rigorously done explaining why this is sort of an educational joke. And now, 10 years later, any article in fMRI brings up the salmon study of why we are skeptical about the whole field. Right. So even, I feel like they really did it right. They weren't critical. They weren't saying everything is wrong. They were trying to do it correctly. And it's still sort of this lingering thing of, well, fMRI is bad because they found activation in a salmon's brain. So it's just so hard to find that clean balance of how to be critical while not letting something negative get way out of context.
I totally agree. So I don't think they did anything wrong. I thought it was hysterical. I was at that poster. I mean, it's a noisy system. Anything you do, it's sort of a butterfly wings. Every once in a while, you did something that inadvertently contributes to something that was really bad. Are you going to blame that person for doing something that was innocent? No. Are you going to keep you up at night? I would argue no. But there's some things that it's more easy to see the causal path between what you did and the thing that happened. So it's just worth a thought, I think. All right. Thanks a lot, guys.